of a technical overview of like the features, how all of this works, and some examples at the end. So what problem is React Native actually trying to solve? We know that with native apps, let's assume we only want to build iOS and Android, we have two apps, that's twice the dev teams and twice the cost. We need full rebuilds to actually see some changes. I mean, there are, I guess, previews in some tools. So like I think SwiftUI has a preview. Some other native builders have previews as well. But to actually see the full change in your full app, you need to rebuild the app. And the same thing goes also for updates. So you need a full rebuild to actually ship an update to the App Store. And native languages are kind of more complex than JavaScript. I think that's actually an objective opinion, not just not an opinion, that's objectively a fact, I guess. So yeah, native languages have threads. You have some imperative UI languages. So for example, if you don't use SwiftUI on iOS, you might use UIKit. You can use either storyboard or like actual the imperative UI way of doing things, so like add view and constructing view and all of that. Objective-C, I mean, this is you don't really use Objective-C if you build a native app nowadays, but still, lots of legacy libraries in Objective-C. Plus, you have hard crashes. Depending on what framework you're using, a hard crash can kind of be very annoying, right? So you see, like, signals, for example, like a SIG abort. Everybody has seen that. You have exceptions that kind of halt the whole execution of the app instead of showing you a nice little dismissible box. So yeah, those are problems. The solution or the theory to solve all of this would be to share as much of the code as possible, so that we ideally have only one dev team with only half the cost roughly of like total, I guess, cost of developing an app and dev team costs and everything. Plus we want to have an interpreted language that runs the business logic. The benefit of an interpreted language instead of a compiled language is that the code can be swapped and reloaded at build time. Because, an interpreted language, is everybody familiar with what the difference is? Yeah, looks like okay. The code can also be updated over the air in production. So if you're familiar with code push, for example, you can actually upload the bundle to a server and the app can actually pull it, on the next app restart, I guess. So that users can receive updates over the air. You can do A and B testing, I guess better, with feature flags and all of that. The code can also be simpler. This is kind of subjective, but yeah, in my opinion, JavaScript is definitely simpler than Swift or Objective-C or C++. You can, and then obviously you still need the possibility to call into native APIs for, at any point to provide native platform features. Because you can also build a website, but then you can't have full control over the native platform because a website is kind of like more sandboxed. So we want to find a hybrid solution here. Yeah, this is where React Native comes in. Yeah, React Native has an architecture for that kind of allows you to write the interpreted language and call into native platform APIs. And as I said before, React Native apps are kind of sandboxed apps. You have a sandbox environment and expose a few functions that you can actually call from JavaScript, and they kind of handle all of this stuff on the native side. So how this whole thing works is the native app is started. So your React Native app is still a native app. It's a fully native app that runs, I guess, a sandbox environment to execute your business logic, which is in JavaScript. The JavaScript bundle is then executed, as I just said, and the JavaScript bundle or JavaScript itself can access any native platform APIs that are exposed or injected, you could say, into the JavaScript runtime. So before the runtime starts, you can inject stuff in there. We're going to take a look at that in a second. Okay, we're actually going to take a look at this now. Calling into native APIs. So because JavaScript is an interpreted language and very different from C++ or whatever native language you use, you can't simply call any function. Calling functions is quite complex. If you know C++, there's many magic things like the V table, for example, that allows you to create virtual functions and everything. And you can't directly link against a function, so you have to have some way of actually bridging between, I guess, languages. Right, so a native function to be callable from JavaScript has to be wrapped as a JavaScript callable function. And it can have a native implementation. So this sounds a bit complex. We know that we need a binding layer to bridge between JavaScript and native. But why can't we just call everything from JavaScript? This is because obviously in some cases, I think I have an example actually in a second. Okay, that's in one other slide, hold on. So yeah, we need a binding layer, as I just said, between C++ and JavaScript. The types, yeah, that's another thing. So you can't directly call a native function from JavaScript because you also can just represent any type in JavaScript. For example, JavaScript values work very differently. They are kind of comparable to shared pointers in C++, and you don't use shared pointers for everything because there's different memory management concepts. In JavaScript, it's garbage collected, and all those kinds of very specific details that are, not compatible with each other. So, as an example, the console.log function on the browser actually works that way. So you can't just, I guess, log to the browser's logbox. That's not something that's exposed to, or that isn't implemented in JavaScript. So you need to bridge between that. And this is, I think it's Safari or Chrome or something like that, where the browser is implemented in a native language, obviously. And then to actually call log, the implementation of log can be called from JavaScript, but it has a native implementation. So as we can see here, there's native code as an implementation. If I console.log, it prints the native code. Or it prints native code, not the native code. Because it doesn't know its implementation, it's not JavaScript. Right, so how do we actually call into native code? In React Native, back when it was released, they came up with the idea of creating a bridge between JavaScript and native in this context is now Objective-C and Java. And they called it RCTBridge. So RCT, that's the iOS name. RCT stands for React Bridge. And when I say bridge, I don't always mean exactly this React bridge. Bridge is in general just bridging between two languages or just two things in general. Right, so with the React bridge, let me read that first, sorry. Yeah, exactly, so okay, with the React bridge, you have your native modules that are exposed over, or I guess in JavaScript, using the React bridge, and the React bridge is responsible for actually managing the whole communication back and forth. Meaning you can call a native module, and a method that you explicitly expose from native code to JavaScript, you can call it in JavaScript, and the same native module can also call back to JavaScript, either through event invokers or return values. Return values are kind of a different thing because the whole architecture of native modules, of the legacy native modules, is that everything is asynchronous and everything is called back using a promise resolver. And there is one exception to this. There's one synchronous method. I think I'm actually going to go into more detail on that later, but we'll see. Right, all method calls are actually batched because the bridge is asynchronous. So that's another, I guess, implementation detail here. The bridge is actually batching all calls. So when you call, let's say, I don't know, native log, as an example in the browser, it doesn't directly call this method and then go to the next line in JavaScript when it actually completes execution, but rather it schedules this call for execution, so it batches it, and then executes it on another thread at any given point later. This is usually pretty fast, but at the same time, if you do it a lot of times, if you do a lot of native module calls, this can be, I guess, relatively slow. So, performance is always relative. Right, and then, as I said, it's promise-based. You execute on a separate thread, right? And if you want to return something to JavaScript, you resolve the promise, which is kind of like a callback. So this is as an example, or actually not an example, this is the React Native core code, where they actually inject the native modules. So this is the native module proxy that they actually assign to the global namespace. Yeah, it's just one big object containing the native modules, and this is where you can actually, I guess, what's actually exposed to JavaScript. Right, so types. How do we pass types from JavaScript to native? You can just pass, let's say, a JavaScript number to native, and it doesn't know how to read that number, or string, or object, or array. So there has to be some kind of mechanism in the bridge here that actually translates values from one language to another. On iOS we have Objective-C, and on Android we have Java. And to pass a JS value to the native side, we actually go through a few steps here. So on iOS, we have this C++ layer. I mean, we have the C++ layer on every platform because the runtime is implemented in C++. So you have to go from JavaScript through C++ at some point. And then on iOS, you can go from C++ to Objective-C++, and then Objective-C, which is relatively cheap. So you don't really have any runtime or no like additional bridge in between C++ and the native language. So it's relatively cheap to do that. On Android, it's a bit different because you have to go from C++ to Java because you want to write your native modules in Java. And there's an additional bridge in between there because Java is more similar to JavaScript than to C++ because it's not directly compiled to binary code in that sense. It has still a VM and everything. So there's an additional bridge in between there. You have to go from in this situation, from JavaScript to C++ using JSI. And then from C++ to Java using JNI. So that's a Java native interface. Right, so for the bridge, we use JSON. So all values that you pass in from JavaScript to native are actually just JSON stringified, which itself is really fast. JSON is really, really fast. Let's see, and yeah, on the native side, we deserialize all of the values then. And also this kind of implies that there's a limitation here so that you can only actually pass along serializable values. Yeah, so the bridge is fairly simple to set up. They have, their own, I guess, supported types, bless you, their own supported types and everything set up. They have a point where you can hook into and set up your native module. It's fairly simple to set up. And it is, even though it's kind of a weird architecture because everything is batched and asynchronous, so it's not as straightforward in terms of how it's implemented, but rather simple to, I guess, use it. And all bindings are generated automatically, so they are resolved at runtime. You don't have any types built at compile time. What are the downsides of the bridge? The design isn't very flexible, meaning you can't, as an example, pass any arbitrary types, so only serializable values. You have no real synchronous method invocation, except for one, I guess, special export. So the bridge has this thing called RCT extern blocking synchronous method or something like that. But we don't talk about that stuff. That's a bit weird. It is slow because, and slow is obviously relative here, because everything is passed through JSON instead of direct references. It is batched and always asynchronous, meaning that, yeah, you don't have real-time native method calls. I guess one other benefit that kind of is implied by this whole asynchronous thing is that you can actually bridge it through a proxy, meaning, for example, if you have a development server set up, like a debugger in Chrome or something, you can actually bridge it through there. So yeah, that's, I guess, another benefit here. You could just do it over the network or something like that. Right, no custom types. I already said this for the first point. You can't really pass any, like, for a vision camera, for example, you can just pass a frame along with, which is like a 10 megabyte GPU buffer, because it's not really serializable, and you don't want to serialize 10 megabytes. You have no pure C++ native modules, so all of the native module APIs that are exposed to users building native modules are in Objective-C and Java. There's no real, I guess, C++ interface for all of this. Over-engineered, yeah, the bridge has lots of code. So yeah, what exactly is JSI? So JSI is the JavaScript interface, and it is one API, or it is, I guess, one interface for multiple runtimes. So the goal of JSI is to provide one interface that you can work with as a developer, and it is not runtime specific. You can use it for, do you have examples here? Yeah, I think I have them. You can use it for JSC, for Hermes, for even the Microsoft Chakra, or whatever it's called, for many different runtimes, as long as they implement it. And yeah, you have lots of different types, so all of the JavaScript values can be represented in JSI values. And JSI values here, the types are C++ types. So we have a JSI value, actually I think I have a, yeah. So a JSI value can be either, that's an actual hierarchy of JSI values, it can be either a Boolean, a double, so that's number, all numbers are doubles, a string, or an object, and an object can be like any key value dictionary of multiple JSI values. That's again, recursive, or a C++ host object with an actual C++ implementation, or a JSI array of JSI values again, recursive, or a JSI function, and a JSI function can have a JS implementation or a C++ implementation. Yeah, so with this type, you can basically represent anything. There's also some special types here, like there's a JSI pointer, for example, which is kind of like, the object anyways, but there's some additional things like, I guess array buffer could also fit under object, which has an actual array, or I guess an actual void buffer that you can actually use in C++ if you want to. And this is actually from, I can't remember if it's reanimated or vision camera, where I convert one Objective-C value into any JSI value. So for example, if it's nil, we return undefined, string, we return a string, number, blah, blah, blah. Oh, frame, okay, this is vision camera. Yeah, so this is kind of like the big if, and this obviously also goes the other way around. Host functions. So a host function is a JavaScript function, or a function that can be used in JavaScript with an actual C++ implementation or native implementation. For example, here it's a lot of boilerplate code, as you can see. We have this one C++ function which captures this, and we have 4 parameters. We have the runtime, any, is that that's a this value, so the function this thing. We have any parameters and the count of parameters, and it returns a JSI value. And then we can just create a host function from that function, and this host function is then a JSI function which you can use in JavaScript. Lots of boilerplate code, you don't need to read all of that, but just so that you know this is how it looks under the hood. And this also implies that you can return JSI values. This also means that you can call, I guess, a native C++ function that is exposed through JSI synchronously and get a result back before, I guess, or it's still, a synchronous invocation. So you're not just batching something, and you can actually return stuff there and use it in JavaScript. Right, so yeah, called synchronously. It is more closely aligned to how normal JS functions work, because it is kind of like a JS function that has a C++ body. And yeah, you have full flexibility there. So you can, for example, use, I don't know, you can access the global namespace. You can get like global.promise, for example, if you want to construct a promise in the C++ function. And you can just run any C++ code in there. Yeah, and this is actually how turbo modules are also implemented. They use JSI under the hood, and they spawn promises if a function is asynchronous. They run stuff on another thread, resolve the promise on the JS thread again, and they implement all of this kind of logic for you, so that you don't have to do it manually, right? As I said before, it's a runtime interface over different JavaScript runtimes. We have Hermes, for example. A JSI value can be a Hermes : VM : Hermes value. Same for JSC, same for V8, same for any other runtime. And if you want to build a runtime yourself, you can actually implement JSI as well, and then you can use your runtime in React Native. Yeah, but I don't think we want to implement a custom runtime, do we? So, benefits of JSI. It is, as I said before, you have instant function invocations. So you call a function, it is synchronous. It is not batched. You can get a result back immediately. You can use it immediately, and it works kind of like if you call a normal JS function. You have more control of the runtime. This is kind of, I'm not sure if you need that at some point, but you can actually, I don't know, use a function to create worklets, for example, very specific things that you couldn't do before. And it is fast, it has very low overhead. Obviously, using the runtime directly, so like Hermes function or something like that would be quicker, but the benefit of JSI is that it's runtime independent, I guess. Some downsides, yeah, it is complicated. It's a C++ API. We don't really want to use C++ for native modules. And it has lots of boilerplate code, as we saw before. The whole function, creation is really, really complex. And it is C++, so to actually, I guess, use JSI, you require some additional bridging. If you're on iOS, this is kind of simple. You have this one function that I showed you before, the if thing, where we convert, I guess, Objective-C NS values, NS means next step, to C++. On Java, this is more complicated because you need to use JNI again. So bunch of conversion stuff. Right, just here a quick note, JSI versus JNI, that's not the same thing. JSI is for JavaScript, JNI is for Java. And yeah, JNI is actually used a lot in React Native apps because there's lots of C++ code, for example. Yoga is implemented in C++, you need to bridge between that. Yes, so as I said before, no runtime interface required for iOS bridging. Yeah, turbo modules. I'm not going to go into detail how you can actually implement turbo modules. This is more like a high-level overview of what you have, available, I guess. So turbo modules are kind of the new native modules. They will eventually replace the old legacy bridge modules, however you want to call them. And they're, again, written in platform native APIs. So you have Java for Android and Objective-C or Swift for iOS. This is way simpler than JSI if you would use C++ directly, but it still provides you the benefits of JSI because it is based on JSI. So the entire bridging layer is generated using C++ for using the JSI APIs, and you write your platform-specific native code. Let's say you want to, I don't know, implement a vibration method in Java or Objective-C, and then the whole turbo modules architecture is responsible for generating the type bindings, injecting it into the namespace, into the JavaScript runtime, and making it callable, and I guess parsing all the types as well. Right, so we have code gen as an extra part of turbo modules that actually generates the type bindings for you. Yeah, it's faster because it's based on JSI, no more batching. It is, I've put an asterisk here because it is not as much faster as everybody thought it would be. But then again, the bridge was just more mature, and this is just, I guess, kind of new still. So it's gonna get faster. Synchronous methods, yeah, we can finally implement fully, safely synchronous methods. We have the bindings generated at compile time. This is a huge benefit actually because let's say you're using code push and you want to update the bundle over the air, but then you have a native module change. For example, I don't know, you use a new native method or the native method name changes or something like that. You want to find out at compile time and then have maybe you can have a script or something that actually tells you, okay, I now need to push a native update as well instead of just a bundle change. And that's why I guess compile time generated bindings are helpful. It's, yeah, typed, so your interface actually has, you can import your interface in JavaScript and it has types. The downsides are that it is a bit slower than JSI. That's obvious, I think, because there's an additional abstraction over JSI, so you can't really match the pure speed of C++ JSI, I guess. But it's still, fairly, really fast. So yeah, moving something to native code. You have a few, I guess, reasons to move something to native code. In general, you should do as much in JavaScript as you can, unless it's like really complex to do so. So yeah, I've put some points here and some examples we're going to see in a second of when it actually makes sense to move something to native code. For example, when it's not possible in JavaScript, when you simply can't do something in JavaScript, then you need to move to the native code. I think that makes sense. When it's a web API that could run on device, this is kind of like a architecture choice, right? Maybe you have a web API, maybe it's so simple that you actually want to run it on device, maybe you don't want to depend on the web API, and it's not slowing you down too much, then you just move it on device. When it's too slow in JavaScript, this is kind of like it's hard to find the exact, I guess, step or point when you actually want to move something to native code. But we're also going to take a look at that in a second. When you need JS runtime access, I don't know, this is just a really rare example. I don't think you're ever going to need this, but like for example, for reanimated or vision camera, it was actually necessary that we need access to the runtime. And when it's a native view. Okay, so when it's not possible in JavaScript, for example, we want to have the phone, or we want to vibrate, I guess. The phone should vibrate. So in this case, we can't, let's say there's no API for this right now. We need to implement it on a native API because JavaScript does not have a vibrate function yet. So we create a new native module. We create one method, expose it. It's called vibrate. Maybe it doesn't even take any parameters. It doesn't return anything. And then we we expose that using one of the native module APIs that we talked about. and we call it from JavaScript. So in this case, it has simple code. It's only one function. It's not called very often, so it's not really performance critical, I would say. You call vibrate once in a while. The code is platform specific because you need platform APIs, so Objective-C or Java, and you don't need to interact with the JS runtime. So this can be built using all three, I guess, options that we have. So native modules, turbo modules, or JSI. It is recommended that you use native modules or turbo modules for that, because using JSI would just mean an additional step to bridge to the native APIs, and that's not really required here. Another example, C++ key value storage. So like React Native MMKV, for example, we have a native class actually, and then the class has methods like get and set, and everything is kind of instance based. So this is like a weird situation because we want to expose the whole class and we want the user to be able to instantiate the class. And having it instance based kinda means that we can't really use native modules for this because we need context for the class. So in this case, it's actually recommended to use JSI because you can create a host object for this, and the host object then has context for, I guess, the specific storage instance that you want to use. So if you want to check out how that works, check out React Native MMKV source code. Yeah, you can also build this using native modules and turbo modules, but then you have to have some kind of unique ID or something that you always pass along to the get functions because they're just static functions kind of. So you don't really have an instance-based approach then. Right, same, or also it was kind of, I put maybe performance critical there because maybe you want to write or read a lot, and then in this case it just makes sense to squeeze out the extra bits of performance. Image post-processing using AI. You have one function that's called post-process image, and you expose that and you want to call it from JavaScript. Let's say we want to call it from Vision Camera actually. If you want to call it from, actually I don't think I have, oh okay, that's the next one, okay, sorry. So that's just one function. It's not called very often, it's not performance critical per se, meaning that we, for example, only call it after you take a picture. Then it can be built using native modules or turbo modules because you're probably going to use some native APIs for that. Because let's say the image is like a file path, you have to load the file path, do your processing part, and then return any value. So with performance critical, I mean it's not called very often. Maybe the code itself is performance critical, but it's only called like once in a while from JavaScript. So then we don't really need the fast bridging performance. When we have face detection in a camera, yeah, okay. We want to detect faces in an image. So in this case, this is actually a bit of a unique case because we can't really build this using native modules, turbo modules, or JSI because we want to do it in Vision Camera. And for Vision Camera, we actually want to use the frame processor plugin API, which is kind of similar to, I guess, JSI, because you just expose one method, and this is called synchronously, and there's no codegen bindings for this, but yeah. Then another edge case, I guess, working on an array buffer. This is kind of complex because you can't really pass along array buffers over the bridge or over turbo modules. So in this case, we actually also have to use JSI because as of February 23, you can't really pass an array buffer over native modules, over the bridge, or over turbo modules. And yeah, with JSI, you can actually do that. You can pass it around without copying it. So you can actually pass around references. And when it's a native view, that's also a no-brainer. You can't implement native views using JSI as of today, so you have to use native modules or turbo modules, plus I guess, for example, for turbo modules, you want to maybe use Fabric, and those things require those abstractions over the, I guess, native APIs. So yeah, in this case, you can't use JSI at all, and there won't be any benefit either, because it's all part of the React View Manager. And yeah, so any native view should be native module, turbo module, plus React View Manager. And then the high-level goal of native modules is ideally you shouldn't need native modules. Ideally, everything should already be possible from JavaScript. But then if you actually, so the native ecosystem should provide everything for you. But then if you actually need a native module for some very specific API you're using, for example, and a vendor maybe gave you only native APIs, then it is most of the time it just makes sense to use native modules or turbo modules and not JSI directly. So yeah, the future of native modules, they're only faster than native, turbo modules are only faster than native modules by a small margin. They provide some other benefits though, like synchronous invocations and passing around references. And yeah, I said this before, native modules will eventually be deprecated in favor of turbo modules. And yeah, in React Native 71, turbo modules are actually a lot easier to build because of the new advanced build script on Android. And it will be, so this is kind of like a theory or nothing public yet, I guess. So turbo modules will become much simpler as well, potentially with Swift-based APIs that are similar to, I guess, Expo modules. Yeah, that's about, I think. And thanks. Are there any questions? And yeah, actually, I don't have the chat open. Can you? Thank you. So the Turbo Modules API itself cannot be directly used from Swift, for example. So you have to bridge between Swift and Objective-C. This is fairly simple to do. So you have like, I think it's an .m file, maybe .mm for Turbo Modules, where you just reference the Swift modules, and it's kind of all linked together. So you don't really have a runtime lookup cost like with JNI, but you have to. So to I guess quickly answer the question, you have to create a simple Objective-C binding layer between the Swift methods that you want to bind to the native modules. And on Android, yes, you can. Kotlin and Java is basically the same thing. Yeah. Yes? You mean when you want to when do you want to create native views in turbo modules instead of native modules, or like? So yeah, native views, I guess, makes sense if you have some very specific component. Maybe you, I don't know, have a vendor that gave you a very specific component. Let's say Google Ads, for example. They have one native component that tracks the views and everything, and they didn't implement it in React Native, but rather like in UIKit or Android. What's the UI library called on Android? Android UI? I don't know. Is it Jetpack? I don't know. So either way, so yeah, if you have a native view and you want to, I guess, bridge that to React Native, for example, or I guess second scenario was for React Native blur hash. I'm not sure if you know that library, but this is a specific, like it is an image component, but I need to do the decoding on the native side, and it was just not possible to show an image with, I guess would have passed base 64 around. So it's just simpler in this case to have a native view, I guess, if you have native components already from a vendor, for example. Yeah, I'm not sure if that answered your question. I just said a lot. Yeah, okay. No, because CodeGen generates the JavaScript bindings as well, and I don't think they have to be. So you can either use Flow or TypeScript, but I think you could still they still get generated even if you don't use TypeScript or Flow. So in either way, you get a generated .js file, which kind of exposes all of the native APIs. And then yeah, I talked to Ricky about this, and it is actually fairly easy to implement like a hashing function that actually tells you when there's been a native module change. Yeah, so there's, I guess, three. So in JSI, let's talk about how that works there, because it's just simpler to understand. Let's say you have an image. An image would be like a native UI image on iOS, for example. You can create a host object, which actually contains the UI image as a member in C++ or Objective-C++, and then just pass that around as if it was a normal JSI object. On the bridge, it works differently because you can only use or pass serializable values, and this is a complex type that can't be serialized that easily. So you have, I guess, three ways to do that. First one being just put it in base 64 and then pass it along. This is really slow because of the serialization, deserialization. It's copying all the time, whereas this wouldn't be copying. And yeah, so that would be slow. Then the other approach would be to write it to a file, pass along this file path, and then read it again. That's also really slow. And the third one would be to kind of create blobs, and blobs on the React Native bridge would be passed around as actual, I guess, references or memory addresses almost. So there's the blob instance, that's why it doesn't have a two-array buffer function in JavaScript. It just contains a native number, for example. Let's say we have blob with ID 1, and then if you pass it to native, you can read it using the blob manager, and that gives you the actual binary data. This is also not really a good design because then you can't really access image width, for example, in JavaScript. it's very hacky, a very hacky approach in my opinion. But yeah, so there were three somewhat working approaches for passing images across the bridge as well. So NativeScript kind of exposes everything on the native platform as like, so you would, for example, if you would use UI screen dot window dot, let's say status bar height, for example, you can write exactly this one code in NativeScript and it looks up all of the native methods. I'm not sure how exactly they are linked against JavaScript, if it's actually using similar technology to JSI or if it's actually compile time, or I guess build time linked and typed in the runtime. So I don't really know that, don't quote me on that, but yeah, I think it's very similar to how JSI works, but just exposes everything instead of only specific things. So I can also quickly go over Expo modules. Expo modules uses JSI under the hood as well. They link everything against global.expo modules, I think. So they kind of just build all of the modules that you use in Swift API, Swift or Kotlin. It's a very similar, I guess, approach on both platforms. So that's why it's quite cool, actually. It's more declarative because you declare your functions and then implement them using lambdas. And then it puts everything into the global.expo modules proxy object. But the main difference to turbo modules is that, I mean, first of all, you don't write them like, expo modules in Swift and turbo modules are not in Swift. And the main difference is that turbo modules also has code gen, and expo modules currently don't have that. So meaning that your modules aren't typed in JavaScript then. It's still, you have to still generate the JS bindings for expo modules. Yeah. In that aspect, expo modules are easier to get started with. Obviously, with an added abstraction, there also comes a limit in, or I guess a compromise in flexibility at some point. So you can't really use, for example, JSI primitives, or you can't really do any runtime specific stuff or any weird stuff. So you can't really, implement reanimated in Swift modules, for example, or Expo modules. But yeah, it's absolutely easier to get started with. And then the goal of turbo modules is to eventually also provide an API that's so easy to get started with, so that it can be compared to Expo modules, I guess. Cool. Then no questions. Thank you all for listening.